Oh, man. Oh, all right. So let me ask you this directly from empirical rule. If I had a normal distribution, how many standard deviations would I have to go out so I catch 68%? To catch the middle, one standard deviation. So it would be -1 to 1 catches the middle 68%. Does that make sense what I just said? So this question is kind of backwards from that. How many z-scores out, up and down, what do I have to go to catch the middle? 91%. So draw the picture. You got to trust me on this. The picture will save your ass when you don't know what to do, and it'll make sure you get the right answer at the end. Right? Still people out there like, yeah, whatever, Jeff. Okay, draw your picture. So if I draw this picture, I told you it's normal, right? Thank God. So the middle 91% would be there. That's the middle 91%. So let me make sure this makes sense. If that z-score was -3, that one's got to be 3. By symmetry, the middle means they're equally spaced out. Are you with me? So I really only have to find one of these z-scores. Does the chart understand this area at all? What's the only area the chart understands? Areas that are where? Below a z-score. So I have 2 z-scores I got to find. Well, what's below this z-score here? Well, if there's 91% in there, how much is out there? 80. There's 9%, right? 0.09. And 8. Yeah, okay, good. Some of you guys are getting ahead of me now. Some of you guys are behind. Some of you guys are, whoa. So there's definitely going to be 9% outside, right? It's got to be a total of 100%. There's 91% inside. Must be 9% outside. Must be 4.5% on one side. Let me stop for a second. I didn't change the question, right? I just changed the area I'm looking at. If there's 91% in there, there's 4.5% down there. I could have asked this question instead. So don't feel like I'm cheating or something. I'm not. I'm just taking what was asked and making it make sense to my poor little chart. Right? So my chart can't give me this, but it can give me this, which gives you the same z-score that this guy wants. So when I look up 0.045, where am I going to look for it? Where am I going to look for it?
On the chart.
On the chart. Be more specific. In the body, right? This is an area. That's why it's up there. Always put your areas up here. Put your z-scores down there because they look like each other. That's even. So look for 0.045. Can I see it? No, I got to go down a little bit. Whoop. 0.045. This is the even one. 0.446 is the closest. 0.455, I'd probably take. If you gave me -1.69 or 1.69, I probably would take that too. But you got to get as close as you can, and that's 5 away. But that's only 4 away. So this guy wins. Does that make sense? So make sure you get the one that's closest. If you gave me the other one, you're telling me you essentially know how to use the chart. So you got to be more careful. So what is it then? -1.70. So then what's the other one? Positive 1.70. So if you go out 1.7 standard deviations, you'll catch, in a normal distribution, you'll catch 91% of the data. I like it. 95%, you got to go out 2. Good, that's the empirical rule, right? I like it. Roughly. It actually comes out to be 1.96, but it's pretty close. I like it. So please, see, there was a question about how to use a z-score chart. This is a very fundamental question. That is the kind of question to talk about today, to get it out. It's too late when you start taking the test. I think all of you are like, somebody ask a question. Yes?
You want like to have you got this or can you do something else?
Say again?
Can it be like something else other than these scores right now? Okay.
Yeah, anything.
Like from the book?
Sure.
For homework for section 4.2, I have a hard time doing like the gains and losses, like setting up like your.
Oh yeah, good, perfect. Because a lot of people didn't quite get this Because that's where the lottery problems were, right?
Yeah.
Where is it here? Let's see.
271.
Let's see. Blah 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 blah. I think one that I assigned was, well, definitely number 75. But a lot of people got that one right because it's back there for you. Let's see. The mistake people were making, what was another one I assigned? 72. Yeah, good. So there are situations, namely in this case win or lose, and there could be different ways to win. But then there's values associated with the situation. That's what X is. X is the numerical values. So what do I mean by that? So number 72 says you buy a lottery ticket to a lottery, it costs $10 a ticket. $10 a ticket. There are 100 tickets available to be sold. In this lottery, there is one $500 prize, and there's 100 tickets. One, what did I just say? $500 prize? Where'd you go? There you are. Two $100 prizes, and four $25 prizes. Okay. So how many ways is there to win? There's like
3.
Yeah, there's 3 situations where you win, and these will affect the what of each of those. Since there's 2 tickets that will win $100, that's going to affect the, what's the magic word there? Probability that you actually do that, right? This is twice as likely you win $100 than it is that you'll win $500. You guys kind of with me? Unfortunately, it's also 93 times as likely you'll lose than you'll win $500. But you know that's the way you expect to have anything like this happen, right? They want to make money on their end. The mistake people are making. There's 2 ways to kind of handle this, but I kind of like to adjust the numbers when I go in, so I can lose or I can win 500, win 100, or win 25. So those are the situations. So what's the actual profits from each of those situations? Well, if I lose, it's not 0 because I'm out $10. So it's negative 10. So that's one big thing that, and somebody did this but then didn't adjust the other ones. If you win $500, how much profit? Well, you had to put $10 out. You got 500 in, so overall $490. So this one would become 90. This one would become 15. You just, all of them go down by 10. Why? Because you had to pay $10 to get a ticket. If you didn't have to pay anything, they would all stay what they are, because you'd actually make that much. If each ticket costs $500, that doesn't make any damn sense. If I win 100, I'm out 400. That's, what the hell is that shit? Maybe. Of course, that's the way some games are in casinos, but don't think about it. Just pull that lever or push the button. Now the probabilities of each. That's going to be affected by how many chances there are to do each thing. So there's only one chance to get $500. So 1 out of 100. 1 out of 100 tickets will get you $500. Which one's that? There it is, Jeff. 1 out of 100 will get you this much total profit. For $100, 2 out of 100 is crazy. 2 out of 100. For $25, 4 out of 100. So what's left over for losing? 93. That's what I was saying earlier. It's 93 times more likely to lose than it is to win $500. And then the next thing that I'm missing from some people is work. Work is good. Work is the most important thing. I have a shirt that mentions that fact. So I think it's important to me. I'm going to go tattoo next. I think it's important to me. Show your work. I'm going to show your work. I'm not going to do that though. Sorry. I'm thinking like a weird Boondock Saints math matchup. Veritas math. All right. And now you just multiply and add, right, to get the mean. The expected value, if you played this thing a lot of times, how much would you expect to average each time? That's what the answer means. So if it comes out negative, that doesn't mean you're always going to lose. It just means you're going to lose so much on average. If you do win, you've already lost a lot, right? It kind of averages out to be a negative amount. And that's what it should be for any lottery if they actually set it up right. Because if every person who plays, another way to look at this is, does everybody do that? Well, what's the answer to that one? I can't remember. Was that the one that's -2?
Yeah.
All right. So if you do this work, I'll tell you right now, you should get -$2. Another way to look at this is, if I had 1 million people play this, now that's weird because there's only 100 tickets. So if I have 100 people play this, on average, every one of them is going to lose $2. I know somebody's going to win, but the other one's going to lose 10, 10, 10, 10, 10. You kind of with me? So how much money am I actually going to end up, once I pay out all the winnings, how much money do I end up with? If I'm the one doing the lottery, 100 times 2, I end up with $200. Each person who plays this can expect, on average, to lose $2. Well, where does that $2 go? To the people they're buying the tickets from, right? So do you understand? When they buy a ticket, they give me $10. But at the end, I got to pay these prizes out. But I'm still guaranteed to have $200 profit on my side. That's how you set up a lottery. That's how you set up a game in a casino. House always wins, because even if they're paying that guy $1 million, there are 2 million people that are playing in these casinos, losing money each one. I'm like laughing. Here's $1 million. Take it. I got 18 million right over there right now. It's still fun. Not this shit, but poker stuff. This is just depressing. I'm sorry. That's basically my impression of everybody's. That's my impression. Sorry. If you do that, that's not what you look like. Most people do. I'm sorry. All right. If you've been to a casino, you know what I'm talking about. You don't even have to pull the lever anymore. It's all this button shit. I mean, before you at least had to do this. You were getting some exercise. No, it's just. All right, go for the free drinks. That's the best thing. Push a button, get a free drink. Is awesome. All right. If you guys don't ask questions, I just go off on weird tangents. Anything else happening? What really gets me depressed when I give this test, I'm saying the average on this test is pretty good, but the people that miss it, they just can't do any Z-score problem, like the basic Z-score problem. Let's do a couple of those real quick. It gets me really depressed. Because this you've got to know. If you don't know how to do a basic Z-score problem, you can't do sample size 30 and you adjust the standard deviation, that kind of stuff. So you can't do that. So what do I mean? I mean, let's say that the average winning somewhere where it was $150 with a standard deviation of $20. And I know it's normally distributed. So what's the probability if I pick, let me put it in English, pick one person, what's the probability they won more than $200? So this kind of problem, and people leave it blank sometimes, and I'm like, this should be your bread and butter. This has to be your bread and butter right now. This should be like, well, yeah, this should be like an order operations problem in algebra. Or at least the way it should be. So in symbols, what does this look like, the question?
Probably x equals greater than 200.
Good. I like it. So this is that standard, you have an X score, you got to change it to a Z score, and then you look up the percentage. Right, that's your standard Z score. That's your what I call the classic Z score problem. No tweaks. I didn't take a sample. I'm taking one person. I'm not asking about the mean. I'm asking about the probability that one person did something, right? I don't have to change anything. So if I draw the picture, what do I put on it? Right in the middle I put
150.
150. Don't put 200 in the middle. That's not the middle. Where's 200 go? It just goes over there somewhere. And then where am I going to shade? Above. All right, greater than, shade above. So I go from the X-score, I make it into a Z-score so that I'm able to use the chart. I like it. So if I make that into a Z-score, what would the formula look like?
200 minus 150.
Good. So it's always my thing that I'm curious about, minus the middle, divided by the correct standard deviation, which is that one. That one works for individuals. Hey, I'm talking about an individual. That jives. I want to use it. Yes, ma'am.
We'll be able to have the Z-score papers, right?
Oh, hell yeah. Right? I was about to go, no, you have these memorized right now. You can have these. I got to remember I can bring some extra just in case somebody forgets theirs. Or if you've written notes all over yours, you don't want to use that. You got to turn them in with your test. So what's that become?
2.5.
Okay, 2.5. So when I look up 2.5 in my Z-score chart, 2.50, I get 9938. Now, I still have people that just put 9938 here. Does it make sense this is 99% of the picture? No, so that's why it's important to know how to draw the picture correctly. It should not be that big of a deal, but it just is a quick visual check. That can't be the end. And I know when I look up at a Z-score, I put that answer below it. Now it makes more sense. Now this big old chunk is 9938. Sorry. So how do you get the actual answer then? 1 minus that. So 0.0062. Was it 9938?
Yeah.
Yeah, okay. That's what I mean. I'm going to give you a problem where I just give you a mean and the standard deviation and say pick one person, what's probably they did this. That's what you do. This is standard, normal little thing. Every problem like this is the same. I'm just going to give you a different number there and a different number there, and who cares? You're going to do the same. You're going to make a Z-score, you're going to look it up, you're going to give me the area. Give me the right area. I like it. Now, the next step, so if you can do that, if I ask you this instead, we take a sample of 11 people. Parentheses, Joe. What's probably that more than that? The sample of 11 people get more than $200 on average. Now it should be harder because if I take a sample of 11 people, where should the average of those 11 people be? It should be close to what? Close to 150. Right? If you take a sample, the average of the sample should be close to the actual average, especially the larger the sample gets. So this answer should be much smaller than the answer we got over there. Oh shit, we already got a small answer. This is probably going to come out to be 0. Let's see what happens. What do I have to do immediately for this before I do anything else? It's going to be exactly the same work as this, except for one little thing. I've got to get the new standard deviation. I got to get, this is the one that works for individuals, but I'm talking about freaking 11 people. So I need the one that works for 11 people at a time. So how do I get that?
20 divided by the square root.
Yeah,
of 11.
the old one divided by the square root of the sample size. Whatever the hell that is. 5.48. Yeah, I'm just making shit up now.
6.0.
Who is it?
6.030.
6.030? So it's exactly the same work, except instead of 20 there, I'm going to have 6.030. And if you do that, you end up with like 8 point something as a Z-score, right? So if I do this work, 200 minus 150 divided by this, I end up with 8 point something. All right, let me stop there. You guys kind of with me there? You can double check me. 200 minus 150 divided by 6.030. What is it exactly?
8.2918.
8.29? 8.2 something? So technically, if you follow what the chart says, what would the chart say about that? Is 8.29 on your chart? No, it's above 3.5 up. And so they say it's always that, which doesn't make a damn bit of sense. I really want this. I know the book I know this chart that I use says this, but why doesn't that make sense? Because the further and further and further and further up I go, the less and less and less and less stuff there is above it, and the more and more stuff there is below it. So it should be like 0.999999 maybe by the time I'm up there. Does that make sense? So I am way up there. I am 8 freaking standard deviations up. So what percent should be below this? Basically 100%. Just about. Not quite exactly, but close enough for a human. So I'd say below this would be about 100%. So how much is above this? About 0%. But if you say 0.0001, it's because you did 1 minus that, that's fine. Because the book says that, or the chart that I use says that. So, oh well, too bad for Jeff. Just pick better, Jeff. No, most of them say that. It's shit, though. Real quick, let me show you one little thing. I don't think I've shown you this yet. And again, what I'm about to show you is a shortcut on the calculator, which is good for checking your work. It is not good for showing me work. I can't remember if I've shown you this yet. Oh yeah, the very first two things. All right, let me slow down. So if you go to second var, so you go up to distributions, that's where you went to get a binomial CDF and binomial PDF. The very first two things, normal PDF and CDF. So if I go to normal CDF, let's see if you guys get this. So this problem is, the mean is 150, the standard deviation is 20, and I want to know the probability is from, and here's where it gets a little weird. I want greater than 200, right? So I'm actually doing this problem right now. We're going to double check this answer. I want greater than 200. So from 200 to what? Theoretically, from 200 to infinity. Because when does this picture stop? Never. But that's not what we put in there. So I want to go from 200 to, just put in 9, go crazy with 9s. That's basically what we call infinity. From 200 up forever, basically. And then I tell it what the mean is. What was it, 150? And the standard deviation. And look, 0.0062. Kick ass. Now, it won't always be exactly the same because we round our z-scores to 2 places, right? So the calculator doesn't round. It just uses all the freaking places. So it might come out off a bit, but it should be decently close if you want to check your work. I guess semi with me. Now, if I want to check this, now I'm curious what the calculator tells me. Let's see if it tells me 0. All I got to do is, the standard deviation is not 20 anymore. It's 20 divided by the square root of 11, right? For the second part. Is that cool? So just change the standard deviation. It's not 20. It's 20 divided by the square root of 11. So now let's see what it says. Oh yeah, dude. Look at that shit. So, what is that? That's 0.16 zeros, 5. You with me? So if you say 0.0001, I'll take it because of the way the chart described. But once you're like 6, 7, 8 standard deviations above, almost everything's below you. Almost nothing's above you. So saying about 0% is actually more correct. It's not 0. I want you to understand. It doesn't mean it's impossible. It just means it's really close to impossible. Right? Probably not going to see whatever this is in our lifetime. Whatever this describes. Yeah. You've heard of like a 100-year or 500-year storm or something like that? Have you guys heard of that phrase before? So that means like on average you get a storm that big every 100 years or something. So that's on average. So it doesn't mean it's been 99 years since that last one. Oh shit. I don't know who these people are, sorry. It just means on average it happens every 100 years, right? So that's a 1% chance of that happening. That's why it takes 100 years for us to see one event. Does that kind of make sense? So that's what this would take. If it was this chance, it would take a lot of years before I see one occurrence of this on average, right? So it's not impossible. It's just really close. All right, enough of that. Sorry. Anything else you want to talk about? What time is it? Oh, we got some time. You can leave anytime you want to, though. You're fine. But you got questions? You guys doing all right? You got a good break? I'm sorry. I always hesitate to ask the question. I always have somebody like, it was horrible. Mine was amazing. It started off bad, but then it got much better. And you're all like, that's good for you, Jeff. Is there nothing else? Are we good? As a group? Are we good? That's fine with me if we're good. Okay.